Welcome back. So we have under our belt all sorts of things about solubility. We know how to do the numbers involved in solubility. The next thing we're going to look at is how come some things are soluble and some things aren't soluble. It turns out that not every ionic compound in the world is soluble in water. Sure, salt is. You take salt, sodium chloride, you put it in water, it dissolves completely, no problems whatsoever. But it turns out that there's some compounds out there that don't dissolve in water. And you're probably familiar with some of them. If you clean your shower, there's usually buildup of grime and goop there. And some of that is some calcium compounds that aren't soluble in water, calcium carbonate specifically. Now, why is that? We can't really get into the details of why, but one of the things we do want to just start thinking about is how can we predict whether things are soluble or insoluble. Now, in an old version of the textbook, they had this table here, and I found this table to be awfully confusing. I couldn't understand what was going on, and I knew whether things were soluble or insoluble. They have these pictures at the bottom of some very beautiful insoluble compounds: cadmium sulfide, iron 2 sulfide, lead 2 iodide. And you can see there's the oranges and the blacks and the yellows and all sorts of neat colors that you can get from these things. Of course, some of the insoluble ones are also white, like the calcium carbonate. So what we're going to try to learn is how can we predict whether ionic compounds are soluble in water or not. And what I'm going to use is a table that's actually from a different textbook. This is from a Pearson textbook called by the author Tro. And I think it's a much clearer table. And you're like, whoa, this is a huge table. Why do we need to know everything in this table? And you don't need to know everything in this table. We're not going to look too much at the stuff down there at the bottom. It turns out if you look mostly at the top, you can figure out just about everything you need in this table. I'm going to post this table so you have access to it on our site, so you can download it and print it out for yourself. But we're going to mainly look at this top part up here, so I'm going to zoom in on that. And what this is the solubility rules table for compounds, ionic compounds in water. So this only works for water, doesn't work for other things, but that's all we care about in this class because the human body, mostly water, lots of things, mostly water. So how do we know if something's soluble? Well, the most important things to know are these first two lines, which is any compound that contains lithium, sodium, potassium, or ammonium is automatically soluble in water. And just to remind ourselves, soluble in water means it can dissolve a decent amount of it. It doesn't mean it's infinitely soluble, which is called miscible. It means that we can put in up to 35.9 grams of salt. That's a lot of salt to put in 100 grams of water, but it's not infinite amounts. So just keep that in mind when we're talking about solubility. It just means that most of it will dissolve, but there is a limit to all of these things. So lithium, sodium, potassium, and ammonium, any salt containing those is immediately soluble. So if I say, hey, is lithium hydroxide soluble? You can say, yes, Professor Clements, lithium hydroxide is soluble because it contains lithium, and all lithium salts are soluble. And what does it mean to be soluble? It means when we put this in water, it falls apart into lithium ions and hydroxide ions. And so we're going to be able to talk about that. Sodium, potassium, ammonium. The anions that are important to memorize are nitrate, NO3-, and acetate. Those are always soluble as well. So even if I have some weird metal, transition metal on the periodic table that we don't use very for, like rhodium, right? So if we have rhodium 4 acetate, and you say, oh, Professor Clements, is that soluble? And the answer is yes. Even though it's got this weird thing that we don't know anything about and we never see, it's soluble because of the acetate, which means it falls apart into rhodium 4+ and 4 acetates. That's what it means to be soluble. The next line is also an important line. It says that chloride, bromide, and iodide are generally soluble. But here we actually start to have some of the exceptions. And what are the exceptions? The exceptions are if you pair them with silver, mercury, 1, or lead. I'm not going to require us to know much about that. I can't completely cross it out though because the homework system does include mercury, and it has to be Hg2 2 plus. So just if you see that, make sure you're looking for that form. But I'm going to focus mainly on silver and lead as our possibility. So what does that mean? If I have some random periodic table transition metal like osmium, and I'm saying, oh, is osmium chloride, osmium 5 chloride soluble? And the answer is yes, because most chlorides are soluble. But the difference is silver chloride or lead 2 chloride is not soluble. And those ones, if we stick them in water, will just sink to the bottom without any of it dissolving at all. The last one to know is the sulfate ion, which again is generally soluble. It does have a few more exceptions. It still has silver and lead, which is what we already know from our chloride, bromide, and iodide, but it also has strontium, barium, and calcium. But if you look at a periodic table, strontium, barium, and calcium are over there on the left, and they are all paired together. So you see strontium, barium, and calcium are in the alkaline earth metals, and they appear together, and so you can kind of remember that they are grouped there. And of course, you'll always have this table available to you as you work on stuff in this class. I don't know why it's moving my table around. So those are the main rules. And what about all those other rules? Those other rules basically just say anything that's not in this rule of things that are soluble is probably insoluble, and it's a great guess. So if you know the things that are soluble, if you can work with the top part of this chart, anything that's not on the top part of that chart is probably insoluble. And you can see, and we'll look through it, things like hydroxides, sulfides, carbonates, and phosphates are among those things that are often insoluble. But there's a lot of complications here and a lot of things going on that we're not going to worry about. Let's just worry about the top half of this table. So let's go over here and we're going to predict some solubilities. Potassium hydroxide, what do we know? If we look over here on our table, we see potassium there in our list, which all potassium salts are soluble. And so this one's going to be soluble, which means it falls apart into K plus and OH minus when we put it into water. Lithium phosphate. Lithium's over here on that list of always soluble, so this one is definitely soluble. Silver sulfide. Well, it's not on our list. The sulfide is not on our list of things that are soluble. It's actually on our list of things that are insoluble, and so we're going to say this is likely insoluble. Strontium nitrate. Strontium, not on our list anywhere, but nitrate is. What do we know about nitrate? Nitrates are always soluble with no exceptions, so this is soluble. Okay. Lead 2 chloride. Chloride's generally soluble right there, but if you remember, lead is one of those exceptions. So the exception means it's not soluble, and so we find that lead 2 chloride is insoluble, which means if we put it into water, it's just going to stay as a solid. It's not going to dissolve. It's just going to sink to the bottom. Strontium sulfate, here it's kind of trickier. Sulfates are generally soluble. Strontium is an exception, and it makes an insoluble compound. I'm not going to probably put too many of those weird exceptions, the sulfate, strontium, barium, calcium, but you should be familiar with them. Calcium hydroxide. Again, calcium's not on our lists anywhere. Hydroxide's not on our list of soluble things anywhere, so chances are it's insoluble. Now, if you look carefully at the list down here, it says the slightly soluble is with calcium. Don't worry about that. We're going to just say it's insoluble and go with it. Go from there. Iron 3 chloride. Chloride on our list of generally soluble. And so this is soluble because iron is not on that exception list. So that's how we predict solubility of individual compounds, individual ionic compounds. But we're going to actually take this one more step in this class, and we're going to start to predict the solubility of reactions of ionic compounds. Now, when I do this in class, I actually have you guys come up to the front of the room, stand up, and start milling around. We don't have that option here, so we're just going to draw things. I do have an example first. I forgot I had a question here. Which compound is soluble in water? So take a moment, look at that list, and see if you can figure out which one is soluble in water. All right. Hydroxide, not soluble in water. Carbonates, not generally soluble in water. Nitrate, always soluble, no matter what you put it with. So we definitely know C. Copper sulfide, sulfides, not generally soluble. Phosphates, not generally soluble, right? We know they're not on our list of generally soluble, so we probably assume they're insoluble, and we end up with C as the molybdenum 1 nitrate. All right, so what we're going to do now is we're going to put into solution 2 different compounds. So what I want to do is I'm going to start with 2 beakers. And in one, I'm going to put some silver nitrate. Now, what do we know about silver nitrate? It's soluble, which means it's going to break apart into its ions in solution. And remember, these ions are all surrounded by water molecules, so they act independently. The silver and the nitrate really not pairing up and talking to each other anymore. And in the other beaker, we've got ammonium chloride. And again, ammonium, always soluble. Chloride, always soluble. So this is a very highly soluble salt. Then what I'm going to do is I'm going to mix these 2 together into 1 beaker. It's got to be a bigger beaker because there's more, right? And what do I have now? I've got a beaker that contains some silver. I've got a beaker that contains some ammonia. I've got a beaker that contains some nitrate, and I've got a beaker that contains some chloride. I've got 4 different ions present in there. When you first mix them, they're acting independently, right? But they're still moving around. This chloride ion's still bumping around. It hits the nitrate every once in a while and says, hi, how you doing? It hits the ammonium every once in a while and says, hi, how you doing? And we have to figure out is when they hit each other, are any of them going to say, hey, I'm insoluble. Let's hang out together. And there's some really easy things that we can eliminate. The nitrate and the chloride are not going to interact with each other. They're both negative ions. So even if they start to get close to each other, they're going to repel each other. Same thing for the ammonium and the silver. As they get close to each other, 2 positive ions just going to repel each other. So we don't have to worry about those guys interacting with each other. We already figured out that silver and nitrate is soluble, so we don't have to worry about that one. We already figured out that ammonium and chloride is soluble, so we don't have to worry about that one. The only set we haven't figured out is these cross sets. Is silver and chloride a soluble combination or not? And is ammonium and nitrate a soluble combination or not? Well, let's start with the bottom one because it's easy. We know all ammonium salts are soluble, all nitrate salts are soluble. So these guys aren't going to interact with each other and do anything because they're always soluble. Even if they got together and said, hey, how you doing? They'd split apart right away and no reaction's going to happen there. But what about silver and chloride? Well, we know that chloride is generally soluble, but we know there's an exception for silver. And so what these 2 are going to do is they're actually going to react in solution and make solid silver chloride. So here on the left, silver nitrate is a colorless clear solution. Ammonium chloride is a colorless clear solution. And when you mix them, what's going to happen all of a sudden is this solid silver chloride is going to form. And that solid silver chloride is going to be a white powder that basically magically forms inside your beaker because silver and chloride, when they meet each other, they say, hey, we're happier outside the water. We're insoluble in the water, and so let's form this solid. And as soon as they form a solid, they're more dense than the water. They sink down to the bottom. So what we're going to do is we're going to write an overall reaction for this. We're going to write a reaction that contains what we started with and what we end with. And so what we started with was silver nitrate, aqueous, means dissolved in water, and ammonium chloride, aqueous, dissolved in water. And what we formed was silver chloride, and that one made a solid because it was on our solubility list as being insoluble. And then we paired up the ammonium and the nitrate. And so this is what our balanced reaction looks like for this particular reaction. How can we do this? Well, one way is always certainly you can draw it. And that's not a bad thing to do, to draw out the different ions, to put them in a beaker there, and just look at the different combinations and decide from your table of solubilities if any of them are going to be soluble or insoluble. Kind of a shorthand way is what I call inside-outside. When we write ionic compounds, we always write ionic compounds with the positive ion, the cation first, and the anion second. And since we know that a cation, silver, is not going to react with ammonium, we don't have to worry about that combination. We know that nitrate's not going to act with chloride. We don't have to worry about that combination. So what we always end up doing when we mix two ionic compounds is our product is the product of the inside and the outside. We're going to make these inside ones ammonium and nitrate. Now we have to rearrange them because even though the ammonium's second here, it has to be first when we write it. And so our product over here is ammonium nitrate, not nitrate ammonia. Always write the cation first. And then we have our outer ones. We have silver and chloride, and that's that product here. So if we do inner outer, the only thing we actually have to figure out, besides the order of things, which is always the cation first, is it soluble or is it aqueous? And that we get from our solubility tables. And so we'll see more examples coming up. But this inner outer is a great way of quickly doing these types of problems. Let's do another set. Let's do some copper 2 bromide and some potassium hydroxide. I'm going to skip drawing the individual beakers this time, and I'm just going to draw my combined beaker. I've got Cu2 plus, right? Bromide is a -1, and there's 2 of them. And I've got bromide ion. I could draw 2 of them. There's no problem with drawing 2 of them, just to keep things having a correct ratio. But we're just trying to determine, is anyone going to interact with anybody else? So when we first combine these two, this is what we have in our beaker. And again, we know the 2 anions aren't going to interact with each other. The 2 cations aren't going to interact with each other. They're each same charge, so they're going to repel each other even if they find each other in solution. We know potassium and hydroxide are soluble because potassium is always soluble. We know copper and bromide are soluble because bromide is generally soluble. So what we have to look here is these cross products, copper and hydroxide, and potassium and bromide. But let's try the inner outer thing here and see how that works. We've got copper 2 bromide, and we know that's aqueous. And we've got potassium hydroxide, and we know that's aqueous. And then what are we going to do? We're going to combine inner and outer. Inner and outer. And what's our inner? Bromide and potassium. Don't write BRK. That's not okay. We have to write the cation first. And it's tempting to write KBr2 because there are 2 bromines here, and you're like, I got to have 2 bromines at the end. But anytime we form an ionic compound, we have to form the correct ionic compound. What's the charge on bromine or bromide? It's a -1. What's the charge on potassium? It's a +1. +1 and -1, we just need 1 of each. So what are we going to do about that 2? How are we going to balance that out? We're going to balance this chemical reaction when we're done. What's our outer? Our outer is copper and hydroxide. And it's very tempting just to write copper and hydroxide like that because that's what's on the left-hand side. But we can't do that. Anytime we make an ionic compound, we have to make the correct ionic compound by looking at charges. Copper here is a 2 plus. Hydroxide is a -1. We know that from our common ion list. So how do we combine a +2 and a -1? We need 2 hydroxides like that. Very important step that a lot of people forget. You have to write the correct ionic compound, not the ionic compound that has just the same numbers as we started with. So now we just have to figure out whether these are solids or aqueous. So potassium bromide, well, that one's an easy one. Potassium is always soluble, and so we know this one is going to be aqueous. What about copper and hydroxide? Well, hydroxide is not on our list of things that are generally soluble, and so we're going to assume, and in this case correctly, that it is insoluble, and we're going to form the solid copper 2 hydroxide. So there's our reaction, but as we noted before, it is not balanced. We have 2 bromine over here, 1 bromine over here, so we need to start working on balancing this reaction. So to balance the bromines, I'm going to put a 2 over here. I now have 2 bromines on the right, and I have 2 bromines on the left. But now I've got 2 potassiums. How do I balance those 2 potassiums? I put a 2 here. And then I check I've got 2 hydroxides, because I got 2 compounds that contain hydroxide. And hey, look, I've got 2 hydroxides over here on the right. And so I now have a balanced chemical reaction. So we're going to write the starting compounds. We're going to do 2, the inner, outer combinations as products. 3, verify that products have the correct formula, that we've done all of our charge balancing that we did here, right? We needed 2 hydroxides to balance out that copper. Then we're going to determine phases. Using the solubility rules. And then we are going to balance the reaction. Those are 5 steps in doing these kind of things. Sounds pretty complicated, and it is. These are actually fairly complicated, fairly advanced chemistry problems that you're doing. But it's kind of cool that you're actually able to predict chemical reactions. And here's a hint too in this class. This is the only type of chemical reaction I'm ever going to ask you to predict. So, hey, predict the products of this reaction. Guess what you're going to be doing? You're going to be doing a solubility type reaction. All right. So those are the 5 steps that you need to go through to do that. So let's just start here. Instead of talking about just bringing these compounds up, let's say, hey, let's predict the products of this reaction. And I'm going to rewrite them here so that I can have some space to do things with them. Actually, let me just give myself a tiny more space. Li2CO3 aqueous plus FeCO3 aqueous. And what am I going to do? I'm going to do my inner and my outer. Now, I have a problem here. I realize this was supposed to be iron 2 nitrate, not iron carbonate. I apologize. Iron 2 nitrate. So iron 2 nitrate there. Do my inner outer. I'm going to combine my lithium with my nitrate. And even though I had 2 lithiums here and I had 2 nitrates here, I only made them 1-to-1 because that's how we do a correctly balanced lithium nitrate. We don't do Li2NO32 because with ionic compounds you always want the smallest possible number, which is 1 lithium and 1 nitrate. We'll balance those out later on. And then our iron and carbonate. And again, 1-to-1 on those ones because iron is +2. I know that because nitrate's -1 and there's 2 of them. And so I've got a +2 here to balance out my iron. And carbonate is -2, and I just know that from my common ion table. So I've got these products now. Now I need to determine their solubilities. Everything containing lithium is soluble, so that is aqueous. How about my iron and carbonate? Carbonate's not on my list of things that are generally soluble, and so I'm going to assume that it's insoluble and forms a solid when I put it into solution. And so now I've got this reaction here. I've got the correct compounds in it. I've got the correct solubilities, and I just need to make sure everything's balanced. I've got 2 lithiums on the left, so I need 2 lithiums on the right. I've got 1 carbonate on the left, 1 carbonate on the right, 1 iron on the left, 1 iron on the right, 2 nitrates on the left, and now I've got 2 nitrates on the right. So this is a balanced chemical reaction. So follow those steps, and you'll always be able to predict these products. Here's another one. Now it's phrased as a word problem instead of a chemical problem. And absolutely, you should be able to do this. This one's kind of the sum of everything. You have to be able to understand these names, be able to produce chemical reactions from them, or chemical equations formulas. There we go. Chemical formulas from them, produce the chemical equation of the reaction, and if you can do all that, you've got this down. All right, sodium iodide. Sodium is a plus, iodide is a minus, and so we're going to make NaI aqueous. Lead 2, Pb2 plus, acetate, C2H3O2 minus. How do we combine a plus 2 and a minus 1? We need 2 minus 1s, C2H3O2, 2. And that's going to be aqueous as well. And we're going to react those and form inner outer. So we're going to form sodium acetate. Right. And I only did 1 to 1 because sodium's a plus 1, acetate's a minus 1. So how do I combine plus 1 and minus 1? Just one of each. And then secondly, my inner, I've got lead with a 2 plus and iodine with a minus 1. So I need to do PbI2, 2 of the minus 1s to balance out my plus 2. Now I got to do my phases. Everything with sodium is soluble. How about lead to iodide? Iodide generally soluble, but there's an exception for lead if you look back at the table, and so this is a solid. Now we've just got to make sure we've balanced this reaction. 1 sodium, 1 sodium, 1 iodide, 2 iodides. So I need to balance out my sodiums here. I'm sorry, my iodides. But now I unbalanced my sodiums. So I've got 2 sodiums on the left. I got 1 on the right, so I need to put a 2 here. Okay, I've got 1 lead, 2 acetates, 2 acetates. I've got a balanced chemical reaction. And this is the chemical reaction of what happens when we add sodium iodide and solid lead 2 acetate are added to water and stirred. Now, this one, if we look back up here, why did I say solid sodium iodide? Just to confuse you a little, I wrote aqueous down here because as soon as I put them into water and stir them, they break apart, and so I have aqueous. If you wrote solids there at the beginning, that would be okay as well. But we have to write this at the end. We've got an aqueous sodium acetate because it's in water, and we've got a solid lead 2 iodide because it's on our solubility tables. These are complicated reactions. You're just going to figure it out by practicing a bunch of them. So I encourage you to work on these and practice these as much as you can. Thanks so much. Bye.